This conference will now be recorded.
Very good evening, students. We have been discussing JEE Mains papers. So JEE Main exam is coming again on this April. So I hope all of you are well prepared by now. We have covered a lot of questions from various JEE Mains papers, and we are at the end part of this paper, JEE Main paper 2021, which happened on 26th August, shift 1. Hopefully, before we go for the exam, we'll be able to cover one more shift of this question paper, second shift. All right, so let us do as quickly as possible. So the first question says, what equal length of an iron wire and a copper nickel alloy wire, each of 2 mm diameter, connected parallel to give an equivalent resistance of 3 ohm? So this is very simple question where you have been given resistivities of iron and copper nickel alloy. So you can see the resistivity for iron. Let me write it as Fe. Iron is given as 12 micro ohm centimeter, and resistivity of copper nickel alloy CuNi is 51 ohm micro ohm centimeter. Rho has got unit ohm centimeter. Okay, resistivity. So you have to find out the equivalent. What equal length? So suppose there are two wires, iron and this alloy. So they are connected in parallel. Okay, they are connected in parallel. So that means you have two resistors. They are connected in parallel. Equivalent resistance is given, but resistances of these resistors are not given. Instead, you have been given the resistivities of the corresponding wires, right? So you have to find out the length of these wires such that you get equivalent resistance of 3 ohm, and the resistors are connected in parallel, as you know. So what we know, R equivalent 1 over R equivalent is equal to 1 by R1 plus 1 by R2. This is the formula for equivalent resistance calculation for parallel combination. Now see, in place of R1 and R2, what I'll write, this, suppose this is having R1 and this has resistance R2. So how to find out R1 and R2? They have told you to find out the common length, and an equal length of both the wire will actually in parallel connection will give this 3 ohm equivalent resistance. So let us find out the length, and let us take that length is L, and you can see the diameter also same for both the wires. So we have got R1 is equal to rho Fe L by A. So these two are actually common or same for the wires. Rho copper nickel alloy L divided by A. right? Now what I'll do here, I'll just multiply this to, like I'll just do this. R equivalent is equal to multiplication of this two divided by addition of this two, right? So this is the thing we have to do. Let me just do the calculation. So we know this is 3 ohm, okay, and see R1 and R2. R1 will be, I'll not put the values first, I'll just try to simplify the formula. So multiplication rho Fe L by area, this is multiplication rho copper nickel alloy L divided by A and whole divided by the addition of these two, rho Fe, okay, rho Fe plus rho copper nickel alloy whole into L by A. See this L by A, let me write here L by A in the numerator. Here then I will get rho Fe into rho copper nickel alloy. Here it is L by A into this. This will be having plus sign, right? So this will cancel each other. Let me put the values of this two. So this is a micro ohm centimeter. So 12 into, so 12 micro ohm centimeter, that means 10 to the power minus 8. I'm writing in ohm meter now. This is 51, okay, 51 into the same power. So I'll write 10 to the power 16 maybe. And here 12 plus 51 whole into 10 to the power minus 8. So 1 10 to the power minus 2 will actually cancel with this. All right. So I'll get 12 into 51 into 10 to the power minus 8 divided by 12 into 51, right? I hope I'm going well with this. I'm sorry, this is actually positive. This is positive. So you get 3 and 6, 63. All right. So I see here there will be L by A. One L by A will be there. Otherwise, how do I get L by L? Like L, how do I get L by A will be there. One L by A will be there in the numerator. So L I have to find out. A is pi square, pi d square. Okay, so see pi d square by 4 I can write when the d is given. D means diameter. So pi d square by 4 we can write. So pi into d square. D means 2 millimeter. So 10 to the power minus 4, right? 2 into 10 to the power minus 2 whole square, pi d square into 4 over here. Okay. All right. So what we can do? 12. See this pi I can write 12 by, like 22 by 7. So 7 is multiplied here. See 4 is multiplied here. Now we have got in the denominator here there will be L. Denominator I have got this 22 here, 4 here, 10 to the minus 4 here, 10 to the minus 8. So 10 to the power minus 4 in the numerator. Okay, now you do this calculation. See this is 9, okay, 17, this is 4, Okay, this four cancel each other, right? So this will be 2, this will be 11, right? So what I'll get, see L, this is just simply calculation, nothing extra concept and all. So L will be is equal to 3, right? So this is 11, this is okay, so 11 into, okay, I think I have put something wrong somewhere. Let me check where I have done that. Okay, so I think let me just do it quickly once again. So 1 over R1, right? Plus 1 over R2. Row 1, let us write row 1 L by A plus 1 over row 2 L by A. So A by L, let us take this common. This is 12 micro 10 to the power 6 here centimeters, so 10 to the power 8 over here, and here 10 to the power 8 divided by 51. Okay, so you'll get here A is pi d square, so L will be coming here 3 into A divided by 12 into 51 into 10 to the power 8 into 63 over here. Okay, all right, so here still I have to put this A. So A is pi into 63 here into 10 to the power 8, and here this pi d square, d is actually 2 into 2 square and 10 to the power minus 4. Okay, so then I get 3, 22, 4, 63, 3, 22, 63, and 4. Here 10 to the power, sorry, 4, only 4, divided by 12, 51 into 7. 7 9 is 63. This will make it 4. This 4 cancels out, and we have 3 threes. This is 17. So what I get, 63 by 17. Okay, 63 by 17. I'm sorry, this is 66. 66 by 17. This will give you, okay, so I think you should get the calculation in cool mind. I'm getting somewhere something wrong. Let me check once again. 12 2 millimeter diameter, that's fine. for everything is fine. Okay, I hope, dear students, you will be better you do this calculation, and let me write what I have got in my notebook, and that is the correct answer for this question. Here I'm again and again doing some mistake. Let me write from my notebook what I have done here. See, L will be is equal to 3 into A into 63 divided by 12 into 51. This is what I am doing every time. Okay, so I have been doing. These are in micro. These are in micro. This is also in micro ohm centimeter. So 10 to the power minus 8. Here 10 to the power minus 8. 10 to the power minus 8. So 1 can be cancelled. 3. So pi d square. Pi d square is 2 square into 10 to the power minus 4 again. So so what you get here, 63 into 10 to the power 8 divided by 12, 15, like this. Okay, so this will make it 10 to the power 4. Fine. So this will make it 4. This 4 cancels each other. This is 9. Okay, so rho L by A. What else we have here? Nothing else. Copper wire. This is given ohm. Fine. Somehow I am missing one 9 over here actually. This is 9. Anyway, if you do this calculation with proper values for everything, rho L by A, I'm taking too much time for this, which is not true. Pi d square by everything was all right. Did I miss 12? No, fine. Oh, it's not my day today with this problem. Anyway, so dear students, it will be 97 meter. Okay, just do the calculation. I'm just rubbing this because somehow I'm stuck but again and again with this calculation part, which is really bad thing. Anyway, you try this. I'll recheck where I was doing mistake in the next class. Okay, so two traveling waves produces the second problem. Let us try to solve this. Two traveling waves produces a standing wave represented by equation this. So let us write the equation of standing wave produced by two waves. So superposition of two waves will produce the standing wave. I hope you know the properties of standing wave, etc. This is per second. So I think this is x maybe. Okay, this is x. Yes, so this is x. We have to find out what is the value of x. Okay. So the question is the node closest to the origin in the region x greater than 0. That means in the positive x-axis, where is the closest node? You know, node will be, see, nodes are actually calculated, positions of the nodes are calculated with this part, See here, how do you understand this is a standing wave? Because there is no omega t minus kx type of argument in the cos or sine. Only you see this is cos x, this is sine of t. That's all. Okay, there is no omega t minus kx, etc. So that actually tells you that the wave is standing, it is not moving. So you know this one, this is, if you just take this as an amplitude term up to this, and this is the time varying term, it is just changing the amplitude, position of the amplitude, that's all. Okay, and I just mean to say, see, if suppose you have a standing wave here like this, sorry, like this is the standing wave. So the position of the nodes are actually not changing, or the antinodes are not changing. Okay, these are not changing, but the positions of nodes and antinodes will be obtained from here. Okay, at different times. Okay, so let us find out the closest node. Okay, closest node near the origin. If I just make this part, okay, cos of argument of this cosine function into x, this to 0, then we will be able to get the value of x over here. Okay, so this I can write cos of pi by 2, because we know cos pi by 2 radian is actually 0. So from both sides I can write 1.57 centimeter inverse into x will be actually equal to pi by 2 radian. Okay, so from here x will be 20 by 7 into 1 over 2 into 1.57, and this, if you do the calculation, you will get in centimeter, and how much you get? You should get 1 centimeter. Okay, you should get 1 centimeter. All right, so this x is then 1 centimeter. All right, so we'll go to the next problem. This problem is again interesting problem. This problem says the electric field in a plane electromagnetic wave is given by 200 cos of uh, 0.5 into 10 to the power 3 divided by m x. That means, you know, this is kx. K is actually 2 pi by lambda. 2 pi by lambda. So lambda has got unit of length, so it is in meter. So that's why this is kx. Excuse me. So the first part, cosine of that is kx. This is kx, and this is omega t. This is omega into t. This is in radian. That means radian per second. That means it is in angular frequency. Okay, anyway, so let us see the question. Question says if the wave falls normally on a perfectly reflecting surface having an area is given, having an area of 100 centimeters square, if the radiation pressure exerted by EM waves on the surface during 10-minute exposure is this much, then find the value of x divided by 10 to the power 9 meter square. Okay, so how do we find out this answer? Or we can actually find out this problem in two ways. There are two ways to solve this problem. Let us do the simplest way. See, the simplest way is to write down the expression for the power not power, pressure, electromagnetic radiation pressure exerted by a particular radiation. If the radiation has got intensity I, then I can write the radiation power exerted by the radiation is 2I by C. C is the speed of light. Now what is this I? I intensity can be written in terms of energy density into C. C is the speed again, speed of light again in vacuum. Okay, so if we put this here, what I get? 2 into I by C, and I'll put U by C, sorry, UC, E into C. This C will cancel each other, so I get 2 into U. Okay, what is this U now? See, this U is the energy density, and I can write this energy density in terms of electric field. Okay, in terms of electric field, I can write half epsilon naught E naught square. Okay, this is the maximum energy or energy density with associated with electric field vector. Okay, or electric field component of the electromagnetic wave. So here, look then, E naught square. E naught is given here, this one. Okay, so half into, okay, so we'll put it here in the pressure expression for the pressure. We'll put in the expression for the pressure. So pressure is 2 into U, where U is actually half epsilon naught E naught square. Half and 2 cancels each other, so I have got epsilon naught E naught square. Let me check whether I have space. Yes, I have space here. So radiation pressure will be given as uh, just epsilon naught E naught square. What is epsilon naught? 8.85 into 10 to the power minus 12. And this E naught square is actually 200 square. Since the amplitude of the electric field vector was 200, okay, 200, and this is, I think, meter, volt per meter, so this is in volt. Okay, so volt unit. Anyway, so what we will get this as in Newton per meter square unit. Okay, so if you do this calculation, how much you should get? you should be able to get 354 by 10 to the power 9. This is Newton per meter square. Okay, this is Newton per meter square. So this is the radiation pressure the surface will actually experience after 10 minutes exposure. Okay, I think this is 10 minutes exposures, right? The question says the electric field in a plane electromagnetic wave is given by the electric field in a plane electromagnetic wave is given by E vector is equal to 200 cos of this. So this is 10 minutes it says, but what we have calculated, I think we have calculated in second. This is 10 minutes. No, I think it's all right. Okay, so what we have found out, we have found out this whole expression. Okay, so whole expression itself we have found out here. So this is, if we compare, we have x by 10 to the power 9 Newton per meter square, right? So then it is x is equal to 354. This is in Newton per meter square. All right. Okay, so we'll go to the next problem. Okay, this is not a problem. This is statement. We have to find out which one is true and which one is wrong. Okay, so by doping silicon semiconductor with pentavalent material, electron density increases. It is true because silicon has, it is 4 valence, like 4 valent, tetravalent. Okay, silicon has 4 valence state. So you know when you have, I hope you remember this, it has like this, so 4 hands, so 4 bonds will be there. But when you have a pentavalent atom, let us say phosphorus or sulfur or whatever, so they can combine. See these 4 electrons, see 4 electrons can actually get involved with this 4 bond, but 1 electron will be extra, so that will be actually increasing the electron density. Okay, electron density. So the statement is true. Then second statement says the n-type semiconductor has negative net charge, net negative charge. Is that true? No, by doping actually we have both ion core, positive ion core as well as electrons. Okay, both positive ion cores and electrons both are there. So we have, see when we dope with atom, pentavalent atom, so this pentavalent atom has a nucleus as well, right? So nucleus will be acting as a positive and 1 electron will be extra. So positive nucleus and 1 electron is actually coming as extra. So both these two will actually make, like earlier also it was neutral, and after doping also the doped semiconductor will be neutral only. So there will be no net charges. Okay, so both, so above statement, so choose the most appropriate answer from the portion given below. So both the statements 1 and statement 2 are true. This is not true. The statement 1 is true but statement 2 is false. This is correct. Let us read the other statements also. The statement 1 is false but statement 2 is true. This is not true. both statement 1 and both are also not false. So you have got B as the correct answer, because see, because pentavalent atom will have one electron extra after the bonding happens with the silicon. Okay, so that will actually increase the electron density. Now let us identify the logic operation carried out by this given circuit. So there are four options. You can see that NAND or NOR or AND or OR. We can actually uh, keep the okay. So let's not remember anything. So this is A bar, right? And this is B bar. This is again AND. Okay, so A bar and B bar. All right. So this will be A bar and B bar. So here there is no A bar, B bar. So see, in case of AND, what we know, both are either both are off or both are on. Let us see whether it is whether it is becoming AND or so suppose I have A, B inputs, and this is a Y output or Z here. Let us write down the Z output. So if both are 0, 0, so I'll get both are on. Okay. If I have got one on, other one is off, then look, on means here it is 0 and this is 1. So this will give you no output. Okay, if 1 is 0, this is on, this is also no output. And if you have both, okay, so I think these are the possibilities. We have to check with this. Let us see. Okay, so identify the logic operation carried out by the given circuit, right? So here is no bubbles. That means this is fine. So we need to know the truth table for NAND gate. So what will be truth table for NAND gate? I think, yeah, so 0, 0, 1 is fine. This is 1, 0. That will be giving you 0. See, we know NAND gate, if you have NAND gate here, okay, suppose this is Y, this is A, this is B. So A and B whole bar, that means A bar, B bar. So A bar, B bar means if you go for both, see one among them, see if this is 1, this is 0. This is actually NAND gate, right? A dot B. I'm sorry, this is A plus B. This will be A plus B. Okay, then get this will be A plus B. That means if you go for OR operation, see if it is 0, then and this is 0. For both 0, you will get 1 in case of NAND gate. In case of NAND gate, you will get, see both 0, 0, you will get 1. One among them is 1, you will get 1. That is also true. If you one among them is 0, in case of NAND gate. In case of NAND gate with this, okay, NAND gate will be with this. The truth table for NOR gate, so how you get truth table for NOR gate? Let us see. NOR gate. So AND gate, see NAND gate is this one. This is NAND. For NAND gate, if both are 0 or one among them is 0, look, this is 0. So this one among them is 0 is actually getting you output. But if both are 0, then also you are both are 0 means 1 1. Okay, 1 1 you are getting that. But if this both are 1 1, you will get 0. This is what, if one among them is 0 or off, you will get output in case of NAND. Okay, so this is not NAND anyway, you can understand that. So it is not NAND. Okay, now we'll check with NOR. So if this is NOR, so let me just give you, no need to mug up and all for solving this problem. So if this is NOR, you have two input A and B. Okay, here suppose this is Y, A, B and Y. Okay, so look this is A, this is output is A plus B whole bar. So A plus B whole bar will be actually A bar B bar. Okay, A bar dot B bar. So this is actually the output we are getting here. So this will be actually a NOR gate. You can see that. Okay, this will be NOR gate, equivalent to NOR gate. So in case of NOR gate, see if I put 1 is 1, another one is 0, you will get 0. If you write both 0, you will get 1. See, then 0 1 will be 0, 1 0 will be 0, and 1 1 also will be 0. So this is NOR gate. Okay, all right. Now this question says an electric appliances an electric appliance supplies 6,000 joule per minute to heat the system. If the system delivers a power of this much, how long it would take to increase the internal energy by this much? Okay, let me write down the options here. The option says you have to find out the time, how long. So it is 4.1 into 10 to the power 1 second. Option B, 2.4 into 10 to the power 3 second. Option C, 2.5 into 10 to the power 1 second again. D is 2.5 into 10 to the power 2 second. Okay, these are the things. So we have to find out the answer for this. So what would be the answer for this? How to solve this problem? Excuse me. Look, this is the an electric appliance supplies this much heat to the system. If the system delivers a power of this much, the system supplies this much heat. This is the rate of heat transfer, or okay, to the system is this much. Okay, so we have to, this is 10 to the power 3 joule. 2.5 into 10 to the power 3 joule, that means 2500 joule. Internal energy has to be increased. Okay, see, for better understanding we should always read the question again and again. So let us read the question. An electric appliance supplies 6000 joule per minute heat to the system. If the system delivers power this much, power means what? Joule per second. Okay, this is joule per minute. Let us write what is joule per minute, joule per second. So joule per minute means, you have to multiply 60 here. I'm sorry, this is 60, just 60. So what we get? Joule per minute this much. So per second, how will be that? So this is P1, say. So this will be 100. 100. Okay. So 100 power it actually supplies to the system. If the system delivers 90, how much time it takes? Okay, we have to find out that. Internal energy, here actually we have to go with this equation. Let us actually write down law of thermodynamics. See, we know dW is equal to dq plus pdv plus, I'm sorry, I am writing just opposite. So dW, or let me write in terms of dq is equal to du plus dW. Okay, here let me write down dq by t delta q by t, delta u by t, delta w by t. Okay, see, this is dq by t. I have to make it 60, see, 6000 by 60, so in second. This side delta u by t, this I have to actually find out, changing the internal energy per second. And this is what this is actually delivers, the power delivers is 90 joule per second. Okay, 90 joule per second, or 90 watt. Let me just clean this portion. So we have got 100 over here is equal to du by dt plus 90 joule per second. So 90 we have got. So du by dt, this is actually 10. This is joule per second, obviously. Okay. So what is the time? We have to find out the time. So du is given already. Change in energy is given. So we'll put that value here and find out the time. Delta u by 10. What is delta u? Delta u is 2.5 here divided by 10 10 to the power 3 divided by 10. That means 2.5 into 10 to the power 10 to the power 2 second. Okay, this is the answer. D. Option D will be the correct answer for this question. So you look, this question is from electricity, but it has been connected to thermodynamics. So these are the beauty of the JEE Mains question. Okay. So we'll go to the next problem. So this problem says, in the given figure, the EMF of the cell is this much. EMF is given, internal resistance is given. So EMF is 2.2 volt and internal resistance is 0.6 volt. If the internal resistance is this, calculate the power dissipated in the whole circuit. Okay, power dissipation in the whole circuit, but we have to know what is the equivalent resistance for this circuit at all. So then only you will be able to find out the current or the voltage across the equivalent resistance, and then we can find out the power dissipation. So look this figure. So this means these two arms, this arm and this arm, are not actually connected to each other. So you look this 4 4 4, this 4 this 4 this 8. Okay, these are actually in parallel combination. Okay, because this is nearly a wire. Okay, now these two along with 8 will be in parallel. Okay, so ultimately, you know what you get equivalent resistance for this, sorry, equivalent circuit for this is, see, this all will be in parallel. Actually, this all will be in parallel combination. Okay, this all will be in parallel combination. You might be thinking how. I'll just tell you how it is. All are in parallel combination. See, this 4 with this 12. Okay, this is parallel, right? And see, this end and this end are connected. So these guys are parallel up to here. So these two guys, so these are two ends again. So this end is connected to this end, and this is connected to this. So this 6 also will be, so 4, this is 6 ohm. Okay, 6 ohm, and this is 12 ohm. At the same time, the 8 ohm, this is 12 ohm. All are in actually parallel combination. All are in parallel combination. Connect here with the battery. 2.2 volt, and this is internal resistance. Okay, so this internal resistance will be in series actually. Okay, along with this parallel connection. So you have multiplication by addition with all of them. Okay, so you just do this. I am just quickly writing the equivalent resistance. We'll get here R equivalent will get here as 1 over 4 plus 1 over 8 plus 1 over 12 plus 1 over 6. Okay, so this will give you, this is one of that. So R equivalent will give you the value 2.2 ohm. Okay, 2.2 ohm. Now to find out the power dissipation, we have got the resistance, so we know, so V square by R equivalent. V square was 2.2 whole square by R is 2.2. Okay, 2.2. This is 2.2. Okay, I'm sorry, there will be one more resistance added to it. It is 0.6 actually. Okay, so this will be 15 by 24. Along with that, you have to multiply, add 0.6. So that will give you here this one. Okay, here there will be 0.6 plus. Okay, so sorry, this, so this equivalent resistance will be this one, and you have to add the, see this R equivalent plus, so total R of the circuit will be this small r, and this total will be actually 2.2 ohm. Okay, so now this will be 2.2, this will be 2.2 watt actually. This is power dissipation. Okay, this is power, so 2.2 watt. All right, so this is actually the answer for this question. I hope there are, okay, so I think there was options here given in this. So options were, let me write in the red ink. So the options were 2.2 watt. Option B was 0.65 watt. Option C, this is C. Option C was 4.4 joule. Sorry, this is watt. 4.4 watt, and option D will be 1.32. So among all this, what we have got? We have got the first one. Okay, so first one will be the answer for this question. Let us go to the next problem. I think, yes. So this question says the fractional change in the magnetic field intensity at a distance r from the center of the axis current carrying coil of radius small a to the magnetic field intensity at the center of the same coil. That means you have to find out the magnetic field magnetic field at any point on the axial axis, and we have to find out the magnetic field at the center and their fractional change. So fractional change means, you know, the delta V by B into 100. This is actually fractional change. So here it is nothing actually. You should write the expression for the axial. So B axial expression, we know mu naught I r square divided by 2 into x square plus y square whole to the power 3 by 2. And B on the center, what we know? We know mu 0 I by 2 r. Okay, so this is actually center. This is at axial point. We have to take the fractional change between these two. Okay, that means you have to do delta axial minus delta center divided by okay, so we have to say this is an axial point. Okay, so this is, no, I'm sorry, this will be at the center. Okay, so fractional change of this to this, right? So this is center. So if we put this, how we get for r less than equal to a radius, then we should be able to get so this will be fractional change, and you know you will get, if you just put this approximation r much less than a, will be able to get nearly 1 minus 3 by 5 r square by a square. So anyway, you have understood this is axial, this is at the center divided by b center. So these things you have to just put. So then this will be the answer for this question. Okay, so 1 minus, I'm sorry, this is 3 by 2, not 3 by 5, this is 3 by 2. 1 minus 3 by 2 is r square divided by a square. Simply just simple calculations. Okay, if you are not understanding, let me write it. Mu 0 I by 2 a minus mu 0 I a mu 0 I a square divided by 2 into a square plus x square whole to the power 3 by 2 divided by mu 0 I by 2a. Okay, so you have to simply simplify this formula, putting this actually, sorry, r is much less than this. Okay, So this will give you the answer, nearly 1 minus 3 by 2 r square by a square, I guess, r square by a square. Okay, so this is the answer for this question. Okay, so with this we have finished this uh, shift to 1 2021-26. We'll just take up next day class onwards the second shift questions of this paper. Okay, so thank you for your patience. Bye for today.